Likewise, as Nicholas Copernicus introduced the heliocentric model, another stunning adjustment in how we interpret the universe could emerge, beginning a conversation known as the rise of cosmology. This development is marked by fundamental aberrations in our assessments and understanding of the universe's significant properties, such as its age, size, and rate of expansion. Neil deGrasse Tyson has noted that the revelation of the James Webb Space Telescope, JWST, has amplified this conversation with observations that challenge materials science. So, what exactly is this crisis, and how does the James Webb Space Telescope contribute to it? Well, contribute may be somewhat of an overstatement. It is more accurate to say the JWST has advanced a study already in progress. The crisis refers to the challenges in how we understand the universe, particularly concerning its age and size, which are intertwined through an extensive framework of scientific interpretations. The JWST has been a game-changer in this context. Before its advancements, our ability to observe the early universe was limited. However, with the JWST's enhanced capabilities, astronomers can now explore much more distant galaxies, providing new perspectives on the universe and challenging some of our long-held assumptions. This breakthrough allows us to look further back in time, closer to the Big Bang, and observe galaxies as they were forming, which provides critical data that can either support or question our current models of the universe. To understand this crisis in detail, it is essential to explore the standard model of cosmology. Known as the hot inflationary Big Bang model or the lambda cold dark matter lambda CDM model, it has been particularly successful in explaining various components of the universe, from gravitational lensing to the structure of the cosmic web and galaxy formation. The lambda CDM model suggests that the universe began with a Big Bang, followed by a period of rapid expansion, and has been expanding ever since. It incorporates elements like dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, every significant observation, especially with cutting-edge instruments like the JWST, raises the possibility that our current model may be insufficient or in need of revision. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at various stages of the universe's history. For example, it predicts that galaxies in the distant past should be smaller, less developed, and contain fewer heavy elements than those in the nearby universe. This is because heavier elements are formed in the cores of stars and distributed through processes like supernova explosions, which take time to occur. Observations have sometimes contradicted these predictions, leading to what has been called a crisis in cosmology. This crisis revolves around uncertainties about the universe's age, as different measurement techniques yield varying results, making it difficult for cosmologists to reconcile these discrepancies. To address this issue, scientists use several methods to estimate the universe's age. One approach involves studying cosmic background radiation, which traces the history of the universe's expansion. Mathematical models, such as the Friedmann equations based on Einstein's theory of general relativity, are used to determine the universe's expansion rate and, consequently, its age. Detailed maps of the cosmic microwave background (CMB), such as those provided by the European Space Agency's Planck mission, offer critical information about the universe's composition. However, these maps lack direct data on dark energy, a key component of the current universe. Another approach involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles because they have a known intrinsic brightness. By comparing their inherent brightness to their observed luminosity, cosmologists can determine their distance and, therefore, the universe's expansion rate over time. This method was instrumental in the 1990s in the discovery of dark energy, which is now essential to cosmological calculations. The Hubble constant, a measure of the universe's expansion rate, plays a crucial role in these calculations. Although not entirely constant, it helps chart the universe's growth since the Big Bang, approximately 13.8 billion years ago. Observations show that the universe has been expanding consistently, and NASA has noted that if this expansion is slowing down, it suggests the influence of an unknown force, possibly dark matter. Recent observations, however, have introduced a puzzling twist to this narrative. The Hubble constant, derived through different methods, yields inconsistent results. Measurements based on the cosmic microwave background, CMB, suggest a value of approximately 67.4 kilometers per second per megaparsec, while those based on observations of supernovae and galaxies indicate a higher value, around 73. These discrepancies have led to what many scientists now call the Hubble tension. The Hubble tension suggests that there may be gaps or inaccuracies in our understanding of the universe's fundamental properties. Some theorists propose that unknown factors, such as new physics beyond the standard model, might be at play. These could include variations in dark energy over time or the influence of exotic particles that we have yet to detect. The James Webb Space Telescope, JWST, has further complicated this picture by observing galaxies that appear more mature, massive, and chemically evolved than what the standard model predicts for their early stage in the universe's history. One of the JWST's most surprising findings is the detection of galaxies with high redshifts, indicating they formed just a few 100 million years after the Big Bang. These galaxies often exhibit characteristics that defy expectations, such as the presence of heavier elements and well-defined structures. Such findings challenge the assumption that galaxy formation was a slow and gradual process, raising questions about the mechanisms that drive early cosmic evolution. To reconcile these observations with the standard cosmological model, scientists are exploring several hypotheses. One possibility is that our understanding of star formation and galaxy growth in the early universe is incomplete. For example, massive stars may have formed and evolved more rapidly than previously thought, enriching their surroundings with heavy elements in a shorter time frame. Alternatively, there may be unknown astrophysical processes at work that we have yet to identify. Another line of investigation involves re-examining the role of dark matter and dark energy in shaping the universe. These mysterious components constitute about 95% of the universe's total mass energy content, yet their properties remain largely speculative. Some researchers suggest that modifications to our understanding of gravity or the inclusion of new forms of dark matter could help explain the anomalies observed by the JWST. The crisis in cosmology is not just a challenge, but an opportunity for scientific progress. As we refine our models and gather more data, we may uncover deeper truths about the universe's origins and destiny. The JWST, along with upcoming observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, will play a pivotal role in this journey. These instruments will provide even more detailed observations of distant galaxies, the CMB, and other cosmic phenomena, helping to shed light on the mysteries that currently elude us. Ultimately, the ongoing debate in cosmology reflects the dynamic nature of science itself. Far from being a static collection of facts, science is a process of discovery, constantly evolving as new evidence emerges. While the current crisis may seem daunting, it underscores the importance of questioning assumptions, testing theories, and embracing the unknown. In doing so, we continue to expand our understanding of the universe and our place within it. Impacting this interaction, on the other hand, if the expansion development rate is speeding up, it could show the presence and effect of dark energy accelerating the universe's development. In January 2018, scientists tracked down something intriguing. Albeit several telescopes showed that the expansion rate of the universe changed depending on the observation point. The Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower expansion in the more distant regions. This discrepancy in measurements highlights the vast size of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, illustrating that the universe is expanding. This discovery was one of the foundations of modern cosmology. Currently, considering the universe's expansion independently of your location, you would observe the same phenomenon at the same speed as the Hubble expansion rate. Initial measurements relied on limited data. However, with technological advancements such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our calculations. Various telescopes use readings of the cosmic microwave background, CMB, to calculate the constant. Despite its reliability, this method has limitations due to the availability of supernovae for distant observations, which restricts our view of the universe. Since the discovery of dark energy in the 20th century, scientists have been puzzled by the inconsistencies between these two approaches to the universe's age and expansion rate. As measurement technology becomes more precise, smaller variations arise, driven by the development of more advanced systems. This progress, however, raises more questions than it provides definitive answers. Although the differences are minor, only 10 to 20 million years separating the estimates. Given that the universe is approximately 13.77 billion years old, they still warrant careful examination. One possible explanation for this discrepancy is the potential for errors in our measurements of the CMB. Despite being one of the most reliable measurements, it has been extensively tested since its launch in 2009 to validate its accuracy. Another perspective suggests a potential gap in our understanding of dark matter, raising the possibility that it might fluctuate over time and be connected to dark energy or another unknown component. This possibility has led to various experimental investigations. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Resolving this uncertainty in supernova models could help address the inconsistencies in measurements. This crisis in cosmology has been further exacerbated by the discoveries of the James Webb Space Telescope, JWST. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. This implies that our scientific framework requires a complete overhaul. However, the problem is that we have no clear starting point to comprehend the scale of this scientific revolution. To explore the universe's origins around 50 million years after the Big Bang, stars, black holes, and star clusters began to emerge, potentially even as early as 50 to 100 million years later. However, these events should be relatively rare. What we don't know is how common galaxies developed later, spanning events between 400 million years after the Big Bang. Recent JWST images reveal galaxies much more distant and therefore older than the standard cosmological model predicts. This divergence suggests that our model needs a significant update. The discovery that the expanding universe relied on galaxies is a major breakthrough. JWST images show galaxies that formed significantly earlier than expected by current cosmological models, triggering a crisis in the field. This issue is related to galaxies and redshift, which is a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This transformed the universe into a soup of hydrogen particles, with some helium and leftover background radiation. The gravity of the radiation then acted on small fluctuations in this hydrogen gas, gradually pulling them together to form the first stars. These early stars, primarily composed of helium and hydrogen, participated in nuclear fusion, creating heavier elements like carbon and nitrogen. These elements played a crucial role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages. In the early universe, gas was primarily hydrogen. Yet as time passed, the gas became enriched with heavier elements produced in stars' cores. This process led to the formation of galaxies containing not just hydrogen and helium, but also carbon, oxygen, nitrogen, and other elements essential for life. These heavier elements, known as metals in astronomical terms, significantly influence the structure and evolution of galaxies. Over time, they facilitated the cooling and condensation of gas clouds, which in turn triggered more efficient star formation. As stars lived and died, they scattered these elements into their surroundings through supernovae and stellar winds, further enriching the interstellar medium. This ongoing cycle of star formation and death, combined with the influence of dark matter, shaped galaxies into the diverse forms we observe today, such as spirals, ellipticals, and irregular galaxies. The role of dark matter in this process cannot be overstated. While it does not emit or absorb light, Its gravitational effects provide the scaffolding upon which galaxies form. Clumps of dark matter created potential wells that attracted baryonic matter, ordinary matter, ultimately leading to galaxy formation. Without dark matter, the observed large-scale structure of the universe would not exist. Another significant factor in the development of the universe is dark energy, a mysterious force driving the accelerated expansion of the universe. Discovered in the late 1990s through observations of distant supernovae, dark energy accounts for roughly 68% of the universe's total energy density. Its exact nature remains one of the most significant mysteries in modern physics. The tension between the Hubble constant, the universe's expansion rate, as measured by local observations versus early universe predictions, adds to the complexity. While local measurements using supernovae and Cepheid variable stars suggest a faster expansion, early universe predictions based on the CMB suggest a slower rate. This discrepancy, known as the Hubble tension, is a key focus of current research, with potential implications for our understanding of fundamental physics. Further complicating the picture are the recent discoveries from the JWST, observing galaxies at extreme distances. Thus, looking back in time, JWST has detected structures that challenge existing models of galaxy formation. For instance, some galaxies appear to have formed earlier and grown larger than our current models predict. These findings suggest that either the standard model of cosmology requires revision or unknown processes occurred during the universe's infancy that we have yet to understand. The discovery of these anomalies highlights the importance of continued observation and theoretical work to refine our understanding of the cosmos. As we peer deeper into the universe with advanced telescopes like the JWST and future instruments, we expect to uncover more surprises. These discoveries will likely force scientists to confront fundamental questions about the nature of dark matter, dark energy, and the underlying physics governing the cosmos. The quest to understand the universe's origins, structure, and fate continues to drive innovation in both observational and theoretical astrophysics. Each discovery not only answers questions, but also raises new ones, propelling humanity further along its journey to comprehend the vast and mysterious cosmos.